So we've been discussing waves in general, and in the last class we started to talk about the principle of superposition of waves, and that led us to the idea of standing waves. If we essentially have reflected waves back and forth along the same medium, we'll get these standing waves. Today, what we're going to do is go a little more broadly into this idea of multiple waves in the same medium and the concept of interference. And we're going to build on our wave model as we have been, where we're describing these sinusoidal waves using this displacement is equal to a sine kx minus omega t plus phi naught. And again, if we have multiple waves in the same medium, we can just simply add those displacements together and they superimpose on each other and get a resultant wave. Turns out the sort of crucial aspect of this wave model in describing these things is what we call the phase, basically the argument of this sine term, right? If we take that whole quantity, we call that the phase. And what matters a lot is if you're thinking about two waves, is the phase difference between 2 points. So if you think about what the phase does, it tells us what part of the sine wave we're on. So if I'm at some position x1 and there's this wave on it, that phase difference tells me if I'm, say, at the maximum or a node or a minimum or somewhere in between along that phase, then that point has some phase defined at that time. Whereas a different point would have a different phase. And it turns out the phase difference, phase 2 minus phase 1, tells us, it essentially captures how those waves line up, right? So if we look at, say, two speakers producing the same note at the same amplitude, the same volume, say, and I'm at a single point, obviously, in the room, how those waves add together are going to determine the sound that I would hear. And what determines how those waves line up is that phase difference. And it's going to be, if they're playing the same note, that phase difference is going to involve the difference in distance I am between each speaker, this X1 and X2. So again, if we want to start to think about how that works, we have those two speakers. They are each described, the sound wave that they produce are each described by their own a sine times a sine of the phase, and the sound wave or the sound I would hear is determined by the sum of those two displacements. Now, if those waves are what we call in phase, that means that they line up. Those phase arguments are equivalent, right? So if I'm at some point here, waves from wave 1 puts me at the crest of that wave, and the same from phase 2. So if those wave fronts are lining up, I'm going to have, a maximum plus a maximum is going to just give me the same sort of wave with twice the amplitude. I have to add the amplitudes of both of those things, and we call that maximum constructive interference. If one way to think about it is if the crests line up from one wave, line up with the crests of the other wave, you're going to have a really quite a larger crest in the wave that you would detect, and you see that maximum constructive interference. They build together. Whereas the opposite end of the spectrum is if you have the waves are what we would call out of phase. So we would have a crest from one source lining up with a trough from another source. And if that's the case, we have, a plus A amplitude wave adding to a minus A part of the other wave, and those can perfectly cancel, and we get what we call perfectly destructive interference. And it turns out you would actually not, in this situation, you wouldn't hear any sound. This is actually how a lot of nice noise canceling headphones work. They actually detect the sound coming in and play a wave out of phase with the background sound and cancel that noise. But those are the two limits. You can have perfectly in phase, as in the arguments of that sine function line up, and they are, so you have crests lining up with crests, and you get a much larger amplitude wave, or you can have crests lining up with troughs, and those waves are out of phase and get perfect destructive interference, where you have, it's essentially no wave. It destroys the wave. You can also have everything in between, right? You can have a crest, sort of just two waves that are sort of out of phase, but not completely. and you can have a slightly larger amplitude because you have a crest lining up with, a positive part but not quite a crest, or anything else in between. And you can have that amplitude of the resultant wave go between 0 with perfectly destructive interference all the way up to 2A, the maximum constructive interference. And today, what we're going to do is we're going to show the math of where this comes from, and how we can sort of think about that. So how does this work? Well, let's say we have, two different waves like we had in that, example where we have some speaker here and another speaker here, just producing sound waves, and we're over here trying to detect those sounds. Well, the speaker one wave is described by D equals A sine kx minus omega t plus the phase constant for speaker one, and the displacement, the wave from speaker two, let's say it's playing a note, the same note, same volume, omega t plus phi over 2, 0, right? And again, this we're just going to call the phase of wave one, and this we'll call the phase of wave two. Now, the total displacement from the waves, the one that you would hear at that location, is just going to be d1 plus d2, thanks to that principle of superposition. And if we sub in what we have there, that is a sine of phi 1 plus a sine phi 2. Or if we want to factor out that a, we just get sine phi 1 plus sine phi 2. Now, there is a trigonometric identity that we can use here to make things a lot simpler, where if I have sine of alpha plus sine of beta, turns out that this simplifies to 2 cosine 1/2 alpha minus beta times sine 1/2 alpha plus beta, right? So we can use this trigonometric identity to simplify this equation, and this ends up meaning that the total displacement is just going to be 2a cosine delta phi, that phi 1 minus phi 2 divided by 2, times sine of, well, this is really just the average of both phases, right? Phi 1 plus phi 2 divided by 2 is the average of those two. So this would just be phi average. And this is what we get. If I want to actually write out that phi average, 2a cosine delta phi over 2 times sine, well, if I average these two phases, I'm going to have the average wave vector, so k average times x minus omega t. If they're playing the same note, it's just going to be omega t, plus phi average. And well, I might as well put average there and be general. So what does this look like? This actually looks like a wave with this being our amplitude, right? We have that sine kx minus omega t plus phi naught. It should be phi naught, average phi naught, where this is our amplitude, and it depends on the phase difference, right? This 2a cosine phi delta phi over 2, the maximum it can be is that 2a we discussed when it's in maximum constructive interference, and the minimum it can be is 0, right? So when does that happen? Well, if we look at, it all depends on cosine of that phase difference over 2, right? That's going to determine how big the amplitude of the resultant wave we're seeing. We're still going to see the same sort of sinusoidal wave. It's just going to have an amplitude that depends on that phase difference. Well, if we think of what cosine looks like, right? It has maximums at 0. It has pi, 2 pi. Remember, it's really just the absolute value here. The amplitude is what we're concerned with. So if that's the case, we can determine that, when this is at its largest absolute value is when this delta phi over 2 is going to be some integer multiple of pi, right? So for maximum constructive interference, let's write max construct, we have that delta phi over 2 has to be some integer multiple of pi, right? Or that phase difference between those two waves has to be 2 pi times some integer multiple, right? And if that's the case, we end up seeing that maximum constructive interference where we have just a sine wave where the amplitude would be 2a, right? And if we go back up here to think about what that means, well, that means that if I'm looking at the speaker for the wave from speaker 1, it looks something like this, right? And the speaker 2 wave would have to have its crests line up in the same way. So I have that crest with a crest. And what that's saying is essentially the path length difference, if omega is the same and the phase constant for both those waves are the same, that this has to be some multiple of 2 pi, i.e. one wavelength between the two, the path length difference has to be a multiple of a wavelength so that the crest lines up with a crest in both of those cases. We can also look at what do we need for perfectly destructive interference, right? So how do we think about that case where we have essentially the waves cancel? Well, that's saying, well, this 2a cosine phi over 2 has to be at our nodes, right? Where we're at pi over 2, 3 pi over 2. This is essentially, when do we have those nodes? Well, we have them at m plus 1/2 times pi with m equal to 0, 1, 2, ... right? If m is 1, we're at pi over 2. If m is, if m is 0, we're at pi over 2. If m is 1, we're at 3 pi over 2, and so forth. So for perfectly destructive interference, we have that delta phi over 2. That argument has to be equal to m plus 1/2 times pi, or our phase difference has to be m plus 1/2 times 2 pi. And that gives us the requirement for perfectly destructive interference. And essentially what this is saying is, much like we had to be for two speakers playing the same note in the same room, if your distance between the two speakers, the path length difference between the two speakers and yourself was a multiple of a wavelength, you had maximally constructive interference. If those were a half wavelength, so if that was lambda over 2, we would have had this situation where we have half a wavelength there, and should have done this in blue, say, where we would have something like this. I'm sorry that I am horrible at drawing waves, but if this path length difference was half a wavelength, we would then have a crest and a trough lining up, and they would perfectly cancel and get our destructive interference. So again, just by taking how we model our waves, adding them together, and we had to use a little trig identity, but we get that the resulting wave from the addition of two sinusoidal waves gives us essentially another sinusoidal wave with an amplitude that depends on the phase difference between those two waves. And we can have those two limiting cases: maximum constructive interference, where if the phase difference is some multiple of 2 pi, we're going to end up with crests lining up with crests and troughs lining up with troughs, and we're going to get a larger amplitude wave. Or we can have perfectly destructive interference, whereas if the phase difference is some multiple of half a wavelength, or this m plus 1/2 times 2 pi, we end up with perfectly destructive interference, where crest lines up with a trough and they cancel. So in one dimension, that's kind of how we've been looking at this. If I have two speakers that are in phase, as in the speakers themselves are both going up when they're going up together and down when they're going together, so they're generating the same note with the same amplitude, and I'm at some distance away from each speaker where that path length difference is one wavelength, I'm going to have crests lining up with crests, and I'm going to get that maximum constructive interference where the phase difference between those two waves is some multiple of 2 pi. And I end up with just a really large amplitude wave where we've added the amplitudes of both of those waves. If that path length difference is some multiple of half a wavelength, I'm going to have a crest lined up with a trough, and those are going to cancel, and everywhere along the wave, the waves line up such that the amplitudes cancel, and I have perfectly destructive interference, and that path length difference is some multiple of pi. That's what it looks like in one dimension. If we think of two-dimensional sources, or we want to plot this in 2 dimensions, if we think of, we have 2 sources of waves here, that are playing, that have the same wavelength, same frequency and everything, and they are, so this blue source is emitting these waves with the blue circular wavefronts, and this source is doing the other ones. We can think of being located, let's say these are speakers, and I'm standing in this open room, and what sort of sound do I hear? Well, you end up with these cool little nodal and antinodal lines where if I'm standing, say, on this red dot, well, I have a crest from both sources lining up. So that's going to be maximally constructive interference. If I'm in between those 2 lines, I'm at a trough for both of those waves. And this sort of defines a line of maximally constructive interference. Whereas if I was on, say, one of these black dots, if I'm standing here, I'm on a crest from this source, but I'm in a trough from this source, and those would cancel, and I would have a perfectly destructive interference. And that, is true for anywhere along this straight line here, where I have these crests and troughs lining up, and everything in between lines up the same sort of way. And I get this nodal line where I have no amplitude on that wave. And you can see these really interesting patterns in this sort of interference here, where they look like this. And again, it works for all waves. If we were to, this is an sort of generated image where I have 2 sources, but you can sort of see these interference patterns. Likewise, you can get diffraction gratings and set up multiple sources of coherent light that will get these interference patterns. A quick Google search and you can find different animations or even videos of this type of thing, but this is an animation of essentially water waves with these 2 sources bouncing up and down. And you can see these sort of nodal lines where there's no amplitude in the wave, and antinodal lines where you have these large amplitude crests. And again, all of that comes down to just the same sort of addition of 2 sinusoidal waves that we just went over. So to summarize, we have 2 waves, both sinusoidal. If they're playing if they have the same wavelength and frequency and same amplitude, when they're added together, we just superimpose those 2 waves, and we end up with the 2 limiting cases: maximum constructive interference, which boils down to the phase difference being some multiple of 2 pi. Essentially, the path length difference is a multiple of 1 wavelength, or we have perfectly destructive interference at the other end where those waves perfectly cancel and you get essentially a 0 amplitude wave. That happens when the path length difference is essentially a half multiple of a wavelength. And those are the 2 limiting cases. You can also get everything in between as well. I kind of wish we were in-person lectures, because there are a lot of really cool demos you can do with this, where you can walk through a room and see these sort of changes in interference patterns throughout the room just by playing 2 notes on 2 different speakers. But if you have any questions about this, feel free to email me. Bring them to the synchronous sessions as well. We'll have a lot of discussion on this and start understanding it. Next lecture, we're going to continue to look at interference, but we're going to look at the situation where, let's say, 2 speakers are playing slightly different frequencies and how that comes into play and affects things.